From a human perspective, Earth feels absolutely giant. Traveling from one side of our planet to the other requires an immense amount of time. From a human perspective, Earth feels absolutely giant. Traveling from one side of our planet to the other requires an immense amount of time. Cosmos operates on a spatial scale that the human brain simply cannot fully comprehend. Within this gigantic playground, alongside billions of small objects, hide true gravitational beasts. These stars burn so violently and grow so large that they render our own sun completely insignificant. Deep within the southern constellation of Scutum, scientists discovered an object that challenges our entire understanding of physics. This is UY Scuti. Meanwhile, inside the Large Magellanic Cloud, another massive contender named WHG64 sits in the darkness. Its precise measurement remains a challenge because of the staggering interstellar distance. Before analyzing these cosmic monsters, we must first establish our primary point of reference. Most of us view our sun as an incredibly massive entity. On the scale of our planetary system, this assumption holds true. With a radius of approximately 700,000 kilometers, the sun absolutely dominates its immediate surroundings. Consider a simple spatial analogy. If the sun were the size of a standard soccer ball, Earth would be 109 times smaller. It would resemble a tiny 2 millimeters peppercorn. Furthermore, combining the mass of every single planet in our system reveals a stark truth. The sun remains 743 times heavier than all of them joined together. Yet, against the backdrop of the wider universe, our star fails to stand out. It is entirely ordinary. Our closest stellar neighbors, such as the binary system Alpha Centauri, share a similar volume. The well-known Sirius A measures twice the solar radius. To understand how far nature can push the limits of stellar dimensions, we must examine the complex process of stellar evolution. To avoid losing our way among the overwhelming variety of stellar types, astronomers utilize an elegant tool developed in the early 20th century by Edgar Hertzsprung and Henry Norris Russell. This system changed everything. The Hertzsprung-Russell diagram plots the surface temperature of a star directly against its intrinsic luminosity. Running diagonals through the center of this chart is a distinct band known as the main sequence. This region is where the vast majority of stars spend the stable portion of their lives. Our sun sits directly within this central band. It is classified as a stable main sequence star of spectral type G. This categorization is rooted in the Harvard system, where type O represents the hottest objects, and type M the coolest. This places our star at a surface temperature of 5,778 Kelvin, giving it a distinct yellowish-white glow. Key to this multi-billion-year stability lies in a delicate state of hydrostatic equilibrium. Every star functions as an arena for a brutal battle between two opposing forces. On one side, relentless gravitation attempts to crush the stellar matter inward toward the center. On the other side, a powerful thermonuclear engine inside the core continuously fuses hydrogen into helium. This process releases vast amounts of energy that push against the outer layers. It perfectly counteracts the gravitational collapse. The sun converts roughly 600 million tons of hydrogen every single second. As long as this outward radiation pressure and inward gravity balance each other, the star endures in peace within the main sequence. A simple rule dominates. The heavier a star is, the higher its temperature and brightness become. A perfect example is Bellatrix, marking the left shoulder of the Orion constellation. Belonging to the hot spectral type B, its surface temperature reaches an astonishing 22,000 Kelvin, weighing nearly 9 times more than the Sun. This immense mass drives up the pressure within its core. It accelerates the fusion reactions to extreme values. This escaping energy expands the star from the inside, swelling Bellatrix to a volume 200 times greater than our solar home. However, such an intense thermonuclear furnace pays a devastating price. While our Sun will live for a total of 10 billion years, Bellatrix burns through its core resources in a mere few tens of millions of years. With only about 7 million years of sustenance remaining, these hypermassive objects are exceptionally rare throughout the cosmic vacuum. Does the largest star in the universe simply have to be the heaviest? Not at all. Physics imposes a strict upper limit on initial stellar mass. This limit sits at roughly 150 solar masses. Beyond this line, outward radiation pressure becomes so destructive that the star violently sheds its outer layers. Yet, the universe occasionally bypasses this restriction through stellar mergers. When two massive stars collide and blend into a single entity, an absolute monster is born. This is likely how the star R136A1 came to be, breaking standard structural limits. Its mass is estimated at 265 times that of the Sun, and its radius is 40 times larger. It belongs to an incredibly rare group called Wolf-Rayet stars. These are objects perched on the absolute edge of existence, just moments away from a spectacular supernova explosion. Our R136A1 emits as much light in just 4 seconds as our Sun produces over an entire year. Its entire lifespan will last a mere 3 million years, a cosmic blink of an eye. Fascinatingly, despite this record-breaking weight, our R136A1 is nowhere near the largest star by volume. Stars with significantly less mass can expand to incomparably larger dimensions. This depends entirely on how they enter their final death throes. When the hydrogen fuel inside a core runs out, hydrostatic equilibrium shatters. Deprived of energy, core collapses under its own weight. This collapse generates a massive spike in internal pressure and temperature. Eventually, core grows hot enough to initiate helium fusion. This new wave of heat travels outward, triggering hydrogen fusion in the surrounding shell. This external energy source rapidly inflates the star, transforming it into a red giant. This exact fate awaits our Sun. In a few billion years, its radius will swell from 700,000 kilometers to nearly 300 million kilometers. The Sun will grow so large that it will easily swallow Mercury, Venus, and most likely Earth. True giants emerge when a star's initial birth weight exceeds 8 solar masses. This takes us deep into the territory of red supergiants. A prime example is Betelgeuse in the constellation of Orion, spanning an incredible 1.2 billion kilometers in diameter. It is over 700 times larger than the Sun. If placed at the center of our solar system, it would instantly consume every rocky planet. Its outer boundary would reach all the way to the orbit of Jupiter. Now we approach the absolute record. Previously mentioned, Uy-Scuti is a red supergiant of such unimaginable proportions that 5 billion suns could fit inside its interior volume. Interestingly, this star is not hot. Its surface temperature is 40% cooler than our Sun. This causes it to emit a deep dim red light because of the vast distance separating us, estimated between 5 and 10,000 light years. Uy-Scuti remains invisible to the naked eye. This star has entered the final stage of its life. Within the next few 100,000 years, it will shed its outer layers to reveal a hotter core. This briefly shifts the object into a yellow hypergiant. These unstable structures can discard an amount of matter equal to the mass of Jupiter in single violent eruptions. They surround themselves with vast clouds rich in oxygen, carbon, and nitrogen. It is from these discarded elements that future planetary systems and potential life will eventually form. A similar process is happening to our second candidate, WHG 64, located in a neighboring galaxy. Recent observations indicate that this star has dimmed dramatically. It has wrapped itself in a shroud of dust it recently emitted. Due to these extreme distances, researchers still debate which of these two stars holds the current volume record. This brings us to the ultimate structural barrier that nature imposes on all stars. This is the Hayashi limit, named after the Japanese astrophysicist Chishiro Hayashi. This is an absolute unpassable boundary on the HR diagram. It defines the maximum radius a star can achieve for a given mass. When a star attempts to expand past this line, convective transport completely dominates its interior. Powerful streams of plasma circulate, like boiling water in a pot. This sudden thermodynamic shift allows gravity to regain the upper hand. It cools the outer layers and forces the star to contract. While future technology may reveal a star that is slightly larger, the Hayashi limit ensures there will be no radical surprises. We have reached the exact point where matter and gravity say stop. Looking up at the night sky, we are peering at objects that have traveled to the very edge of physical reality.